Hello. Today we're going to talk about some properties of determinants. In particular, we're going to introduce Cramer's rule. But for now, let's review some basic properties about determinants and elementary row operations. We're also going to review some basic properties about linear transformations and matrices that we'll be using today. Let's start with an early result, what we call the dimension theorem. Theorem 2.3 says that if we have two finite dimensional vector spaces V and W, then for any linear transformation T between them, the nullity of T plus the rank of T is the dimension of V, the domain. Some texts call this the rank nullity theorem. We then have theorems 3.1 and 3.2. They explain what happens when you have an elementary row operation on an M by N matrix A. Let's say that B is obtained from A by performing an elementary operation. If this were a row operation, then B equals E times A, where E is an elementary M by M matrix. If this were a column operation, then B equals A times E, where again E is some elementary matrix. Third, elementary matrices are invertible, and in fact the inverse of an elementary matrix is a matrix of the same type. Theorem 3.6 gives us a way to bound the rank of a matrix R. If we have an M by N matrix, then its rank R is less than or equal to M, the number of rows, and less than or equal to N, the number of columns. Also, we can find matrices, invertible matrices B and C, where we could take B times A times C to find a diagonal matrix in the form I, 0, 0, 0, where I is some R by R identity matrix. Again, the number of ones here is the rank of our matrix A. Third, both A and its transpose have the same rank. Theorem 3.7 gives us a stronger way to bound the rank of a matrix, given that this matrix perhaps is the product of two other matrices. That is, the rank of B times A is less than or equal to the rank of A, and is less than or equal to the rank of B. Theorem 3.16 has a lot of statements, but we'll just point out the main one that we need for today. Let's assume that we have an M by N matrix where M equals N. That is, the number of rows equals the number of columns. Then A is invertible if and only if its reduced row echelon form is the N by N identity matrix. Theorem 4.4 gives us a way of computing the determinant of an N by N matrix. It says that for any row I, we have the following expression, which is a sum, j goes from 1 to n, negative 1 to the I plus j, times A sub ij, this is the entry in row I, column j, times the determinant of aij tilde. This is that matrix we find from A by crossing out row I and column j. Next, the determinant of A is 0 whenever A has a row of zeros, and the determinant 0 whenever A has two identical rows. Next, remember that we have the concept of elementary row operations. Let's say that A is an M by N matrix. There are three types of operations that we can perform on A. Type 1 says we can interchange any two rows. Type 2 says we can multiply any row by a non-zero scalar. And type 3 says we can add a multiple of one row to another. These are all called elementary row operations, and an elementary matrix is a square matrix obtained from the identity matrix by performing exactly one of these three elementary operations. Theorems 4.5 and 4.6 explain how the determinant changes under an elementary operation. Let's say that B is a matrix obtained from A by interchanging two distinct rows. Then the determinant of B is negative the determinant of A. Let's say that B is obtained from A by multiplying one row of A by a non-zero scalar. Then the determinant of B is that scalar times the determinant of A. And finally, let's say that B is obtained from A by adding a multiple of one row to another. Then the determinant of B equals the determinant of A. As a consequence of all of this, let's say that E is an elementary matrix. If E is obtained from I by interchanging any two distinct rows, then the determinant of E is minus 1. If E is obtained from the identity matrix by multiplying one row by a non-zero scalar k, then the determinant of E is that non-zero scalar k. And finally, if E is obtained from the identity matrix by adding one multiple of one row to another, then the determinant of E is just equal to 1. Today we're going to use all of this and talk about a couple more special properties of determinants. Here are a few consequences based on the results from the previous lecture. Let's say that A is an n by n matrix. Then for any other n by n matrix B, the determinant of A times B is the determinant of A times the determinant of B. That is, we say that the determinant is a multiplicative function. A is invertible if and only if its determinant is non-zero. This actually explains why we've used the word determinant. It actually determines whether a matrix is invertible. In particular, the determinant of the inverse of A is the reciprocal of the determinant of A. And finally, the determinant of the transpose of A is just equal to the determinant of A. Let's begin by proving the first statement here. We want to show that the determinant of a product is the product of the determinant. We actually have two cases we're going to consider: whether the rank of A is less than n or the rank of A is equal to n. So let's assume first that the rank of A is less than n. Then we see that the rank of A times B is also less than n. So we're going to prove that the determinant of A is 0 whenever the rank of A is less than n. Then this would prove that the determinant of A times B is the determinant of A times the determinant of B because all of these are equal to 0. To this end, let's denote lowercase a1, a2 through a sub n as the rows of A. We want to consider that linear transformation that's defined by multiplying by the transpose of A, not by A, but by its transpose. We see that because the rank of A is less than n, the nullity of this transformation is greater than or equal to 1. This means that we can use this to find a non-zero vector in the null space, and hence express one of the rows as a linear combination of the other rows of A. That means that the determinant of A can be evaluated using a cofactor expansion along this row. We'll see here, by multiplying things out, that we actually have a sum. You'll see this on equation equality 3. J goes from 1 to n minus 1 to the r plus j, a sub ij, times the determinant of a rj tilde. This here is the determinant of that n by n matrix whose row r is actually equal to row I. That means that here we have the determinant of a matrix that has two equal rows, hence the determinant is 0. So this does indeed show that the determinant is 0 whenever the rank is strictly less than n. Next, we need to work things out when the rank of A is equal to n. Let's denote the reduced row echelon form of A, RREF. Then we know that we can express A as a product of elementary matrices. So let's consider the following proposition as a function of an integer m. Let's say that A is the product of m elementary matrices. Then the determinant of A times B is the determinant of A times the determinant of B for any n by n matrix B. Let's first establish the base case when m is equal to 1. This means that A itself is an elementary matrix. But then these are just the theorems that we've worked out before. If A is an elementary matrix, we know that its determinant is either minus 1, k, or plus 1, depending on whether it comes from a type 1, type 2, or type 3 operation. Similarly, we worked out how the determinant of A times B transforms in terms of the determinant of B. So in the special case, when m is equal to 1, we do find that the determinant of A times B is the determinant of A times the determinant of B. Now let's assume our inductive hypothesis that the statement is true if A is the product of M0 elementary matrices. We'll consider in the next case where A is the product of M0 plus 1 elementary matrices. Then we can write A times B as an elementary matrix e sub m0 plus 1 times C, where C is a product of m0 elementary matrices times our matrix B. Then the determinant of A times B is the determinant of e m0 plus 1 times the determinant of C, because we just proved that the base case P of 1 is true. Now, the determinant of C we can express as the determinant of e m0 dot 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 e1 times the determinant of B, because we assume that our inductive hypothesis is true. Now, recombining the determinants, we see that this is equal to the determinant of e m0 plus 1 dot 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 e0 times the determinant of B, again assuming that the inductive hypothesis P of m0 is true. But now staring at this, we see that this is equal to the determinant of A times the determinant of B, showing that proposition P m0 plus 1 is true. So this shows the first of our three statements. Now let's prove the second statement. This was the one about invertibility. First, let's assume that A is an invertible matrix. This means that we can find an A to the minus 1 such that A times A to the minus 1 is the identity matrix. According to the first statement, if we take the determinant of both sides, we see that the determinant of A times the determinant of A inverse is equal to 1, showing that not only is the determinant of A not equal to 0, but in fact the determinant of A inverse is just the reciprocal of the determinant of A. Conversely, let's say that the determinant of A is non-zero. We're going to prove that A is invertible. So, by way of contradiction, let's say that A is not invertible. If this were the case, then the rank of A is strictly less than n, so the determinant of A must be 0 by the discussion above. This is a contradiction. Let's show the final statement. We actually have two cases. Just like before, either the rank of A is less than n or the rank of A is equal to n. We want to prove, if you recall, that the determinant of A transpose is equal to the determinant of A. First, let's assume that the rank of A is strictly less than n. As we stated before, the determinant of A is 0. But the rank of A transpose is equal to the rank of A, so the rank of A transpose is also less than n, showing that the determinant of A transpose is 0 as well. Hence, the determinant of A transpose equals the determinant of A because they're both equal to 0. Next, let's say what if the rank of A is equal to n? Then in this case, we know that A must be the product of elementary matrices, and so then the determinant is the product of the determinants. But A transpose must also be the product of the same elementary matrices up to transpose, so the determinant of A transpose is the products of the determinants of these matrices transpose. But now it's an easy exercise to prove that for any elementary matrix, the determinant of E transpose is equal to the determinant of E. This completes the proof. The last concept I'd like to introduce today is what's called Cramer's Rule. Let's take a look at a motivating example. Say that we have a system of two equations and two unknowns. The unknowns here are x1 and x2. Of course, we can express this as a system of linear equations in the form a times x equals b. Assuming that the determinant of this 2 by 2 matrix is non-zero, we found in previous lessons that the solution of this system is, as you see on your screen here. We can expand out to take a closer look at x1 and x2, and we find that we can express x1, x2 as the ratios of these two determinants. We're going to write down a slightly more general statement. Let's say that we have a system of n equations and n unknowns. In this case, we have x1, x2 through x sub n as our unknowns. We can write this as a single equation in the form a times x equals b. Let's assume for now that the determinant of A is non-zero. First, A is invertible, and in fact its inverse is the classical adjoint divided by the determinant. Next, the system has a unique solution, which we can express as the classical adjoint times our vector b divided by the determinant, or we can write each variable x sub k as the ratio of two determinants. The denominator, of course, is the determinant of A, but the numerator is the determinant of a matrix M sub k, where we've replaced column K with the vector B. Let's try to explain where this theorem is coming from. Recall that the classical adjoint is defined as the transpose of the cofactor matrix. The ij entry of this matrix is as on the screen here. We can then multiply this classical adjoint with the matrix A, and we find the following sum. But if we stare at the sum very closely, we see that here we have a sum, k goes from 1 to n, minus 1 to the j plus k, a times ij, remember that this is the entry in row I, column j, times the determinant of a jk transpose. This is the matrix we obtain by crossing out row j, column k. This here is the determinant of an n by n matrix obtained from A by replacing row j with row I. Well, if I is different from j, then here we have the determinant of a matrix that has two equal rows. Hence, the determinant will be 0. But if I equals j, then this here is just a restatement of the determinant of A. Hence, we have the matrix product, A times the classical adjoint, is a scalar times the identity matrix. Since the scalar, namely the determinant of A, is non-zero, we then can divide and find that A inverse is the classical adjoint divided by the scalar determinant of A. Let's now prove the second statement. Well, we already know that our system can be expressed as A times X equals B, so essentially by multiplying A inverse on both sides, we find that the unique solution is the classical adjoint times the vector B divided by the determinant of A. Now, let's simply expand out to see what is the typical entry in this column vector S0. Well, we can expand as you see here on your screen, and we have a sum, j goes from 1 to n, minus 1 to the I plus j, b sub j, determinant a, jk, tilde. Here, we see that we have the determinant of a matrix where we cross out row j and replace in the vector b. We have to be a little bit careful that it's actually B transpose because B is a column, whereas we're actually replacing things with a row. But the determinant of the transpose of this matrix is just the determinant of this matrix. This is a rather strange theorem, so let's just discuss this by going over a couple of examples. First, let's say that we have a system of two equations and two unknowns, namely x and y. We have the following determinant of our matrix A, A11, A22 minus A12, A21. Assuming that this determinant is non-zero, Cramer's rule asserts that the unique solution is as you see here on your screen for x and y. You'll notice that the denominators are just the determinant of A, but for the numerators, they're a little bit different. For x, we've replaced the first column with the scalars b1 and b2, and for y, we've replaced the second column with b1 and b2. Now let's say that we have a system of three equations and three unknowns. Again, we can express the determinant here for this 3 by 3 matrix. And assuming that this determinant is non-zero, Cramer's rule asserts that the unique solution is as you see here on your screen in terms of x, y, and z. Notice that the denominators are just the determinant of A. But for the numerators, they look a little bit different. For x, we've replaced the first column with b1, b2, and b3. For y, we've replaced the second column with b1, b2, and b3. And for z, we've replaced the third column with b1, b2, and b3. Thanks very much for watching.